So the next hour, the tutorial will be offered by Jitin Jose and John Selly from Microsoft Azure. The session is titled Best Practices for Running HPC Applications on Microsoft Azure. Dr. Jitin Jose is a senior software engineer. His work is focused on co-design of software and hardware building blocks for HPC platforms and designing communication runtimes that seamlessly expose hardware capabilities to programming models and middleware. His research interests include high-performance interconnects and protocols, parallel programming models, big data, and cloud computing. Before joining Microsoft, he worked at Intel and IBM Research. He has published more than 25 papers in major conferences and journals related to these research areas. Jitin received his PhD degree from the Ohio State University in 2014. And John Selly is the HPC and AI benchmarking principal manager for the Azure Compute team. He works closely with customers and independent software vendors to aid them in running successfully in Azure. John has been working in the HPC field since 2002, when he joined Pratt & Whitney doing CFD and FEA simulations on Linux clusters. In 2007, he joined the Idaho National Labs and led the HPC user support group there. At INL, he helped also configure clusters and applications for the user community. In 2013, he joined the PBS Pro team at Altair and worked with HPC centers around the world to help them manage their current HPC workloads and design for their future workloads. So let's welcome Jitin and John. I'll stop sharing the slides, so please share your slides and get started.
Thank you, Dr. Panda, for the warm welcome. Let me share my screen and then start. Are you able to see the screen?
Yes, you can go to the presentation mode.
Yes, perfect.
Perfect, thank you. So yeah, thank you. Let's get started then. Here is the overall agenda for the talk. So we'll start with an overview of Microsoft Azure. We'll list out the different Azure HPC offerings, specifically like the IB-based IB-based HPC SKUs. Then we'll focus on the HPC software ecosystems, specifically MapH2 and MapH2X. Here is the meat of the tutorial. We'll be showing how we can easily create and deploy an HPC cluster on Azure, and we'll do a live demo as well. And we'll follow up that with the some of the quick performance results and performance characteristics of MapH2 and MapH2X on Azure, different Azure SKUs. And finally, we'll wrap up with the different best practice recommendations for running HPC workloads using MapH2X and MapH2. Okay, so here are the different Azure regions. So as you can see, I think there are currently more than 60 different Azure regions, like many of these have HPC specific SKUs as well. So this is really literally global scale. You can really go for it, and with a focus on cost as well as performance. Those are the major two things. So traditionally, I think you all know, like when cloud computing was started, the major focus was, like the major use case of cloud was, say, web servers or like running some web applications on the cloud, right? So from that point, the scope has really like widened. So currently, most of the users include really HPC or AI workloads, and to address that, we have really compute-intensive SKUs or memory-intensive SKUs, as well as GPU SKUs. If you compare the performance of those versus bare metal, those are more or less the same. So we'll go over those in detail later. So let me introduce the HPC Fleet in Azure. So here I have included only the IB-based SKUs. So on the left here, so are you able to see the pointer?
Yes, we are.
Yes, Jitin, we can see
it. Okay, great. Okay, great. So, so the H series, that's the HPC or IB only SKUs. And the N series is basically GPU SKUs. And here I have listed only the GPU plus IB SKUs, not the GPU only SKUs. And here is a quick way how you can decode the names and how you can identify what each SKU is. So the first like 1 or 2 alphabets here that specifies the family of the SKU. So for example, HB, this is the AMD ROM family. And the next few letters indicates how many cores, how many the cores are available in the VM. For example, in this VM, there are like 120 VM cores. And here the R indicates, okay, this VM has support for RDMA. And S indicates, it supports premium storage. And the V2, or if there is none, so that indicates the generation of the VM family. So similarly, and here these are different GPU plus IB family. So ND, this is the latest GPU SKUs. So ND family, and we have 40 cores. So this is the Intel Skylake based SKU. So the VM will see 40 cores there. And R, it supports RDMA, and S supports premium storage. So HB V2, it has HDR, and ND40, it supports EDR. So that's a quick overview of how you can decode the names to the actual VM functionality or features. And let me quickly highlight the 2 different SKUs like HB and ND40. So you may be wondering, okay, so if this is based on the AMD ROM, each socket has 64 cores, and why VM is only seeing 120 cores? So here is the answer. So as many of you know, like AMD ROM is actually, the architecture is based on like NUMA nodes, where the NUMA node can be configured to have X number of cores, say 4 or 8, depending on the CCX or CCD configuration. So in this case, the NUMA node has, each NUMA node has 4 cores, and we reserve the 1 NUMA node per socket for the host. That's why the VM is actually seeing 120 cores, so 60 cores from the first socket and the 60 cores from the second socket. And it has the max clock speed of 3.3 gigahertz and memory bandwidth of around 340 gigabytes per second, and like around 4 GB memory per core. And this has the HDR, latest 200 gigabits per second HDR, supported through SRIOV. And similarly, this is ND40. Oh, so by the way, if there are any questions, please ask in between, like we can answer them and in between. So yeah, please feel free to ask any questions in the middle. Okay, so this is ND40. So this has, this is the GPU SKU. So it has 8 GPUs, 8 Tesla V100 NVLink connected GPUs, and each GPU with around 32 GB memory. And it has EDR connected again through SRIOV. And this is a Skylake based queue, so 24 sockets per, 24 cores per socket, and we reserve 4 cores per socket for the hypervisor and the host. And tomorrow we'll be explaining like how we, what are the mechanisms used to partition the SKU, and so please, join that session. So where we will go in detail. So basically, like once you partition, there are no like interference from say VM to the host or from host to the VM. So there won't be any interaction. So whatever cores that you get, so those are like dedicated to you. Though you won't see any like jitter or anything. Is someone asking a question or something?
No, it looks like Harry is not muted.
Oh, okay, sure. Okay, so yeah, moving forward. These are the different network features of, the different SKUs. So HB, HC, and NDV2, all of those use ConnectX 5, which is the EDR 100 gigabits per second IB. And HBV2 and the newer generations will use ConnectX 6. So HBV2 currently has ConnectX 6, supports 200 gigabits per second IB. And all the features that you will see on a bare metal cluster, all the latest features you can take advantage on Azure. It's also, for example, DCT, hardware offload, hardware collectives, where you can get like really good performance for the non-blocking MPA collectives, UD-based multicast, hardware tag matching, like reliability or congestion control using Shield or adaptive routing, like all those features, latest network features you can avail on the cloud also. So any questions so far, or? Okay.
There are no questions in the QA box, so please proceed.
Sure. So yeah, so let me move to the next part. So whatever, how great the hardware can be. Like, if the software is not, there to expose the performance, then what's the point, right? So that's why we have our HPC software ecosystem there. Like we have out of the box CentOS HPC VM images, which includes our favorite MapH2 and MapH2X MPI libraries, which help you to get the best performance out of the box case. So these CentOS images, or the VM images, so one can, when you create a VM or when you deploy a cluster, you can select it from the marketplace. For example, if you search for CentOS HPC, you'll see the different images, generation 1, generation 2, CentOS 7.6, 7.7, 8.1 HPC images. And all of those have the, latest Mellanox software, different MPI libraries, different HPC libraries, such as the FFTW, GLAS, etc. And also the different optimization configurations. Those are recommended by, say, AMD or Intel. So those things are also included in the image. So all these images, or how we configure these images, so everything is open source. If you refer our GitHub repository, so it has all the details. So that is one option. Like you can deploy out of the box VM images, or you can actually bring your own software stack. So you can pick any base VM image, and then you can build or configure your own HPC software stack. You can still use that. And if you want to deploy a lot of VMs based on that particular VM, so you can just create a custom image out of it and then use that for later deployment. So, you have the complete flexibility. Let me focus a little bit more on the MapH2X Azure release. So, earlier last month, OSU released the MapH2X Azure, and these are, available in all the HPC images. And some of the feature highlights include enhanced tuning for point-to-point and collectives. So these tunings are specifically for the HPC SKUs, HB, HC, and HPV2. And it has the XPMM support. Like if the XPMM libraries are installed on the VM, it will take advantage of it. Otherwise, it will fall back to whatever other mechanism that's possible for shared memory or KNM or anything. And DC support, dynamically connected transport support, cooperative protocol, and it can also take advantage of hybrid RC-UD support. So yeah, that's a quick overview. And with this, I'll hand over to John for the for going over the different deployment models and doing a demo. So John, please feel free. Yeah.
All right. Well, thank you all. Are you able to hear me, Jithan?
Yeah, it is. Yeah, awesome. Thanks. Go ahead, please. Yeah.
All right. So yeah, we're now going to talk about how do we deploy into Microsoft Azure and set this up, and then some of the performance characteristics that we got. So first of all, to get onboarded onto Azure, you need to set up an account, then get an Azure subscription, and then request the quota for the environment. So as Jithan talked about the different HPC and AI VMs that we have available, you just need to go on and request that I would like 960 cores of HBV2 or 80 cores of the MD40 RS V3 SKU. And once you are granted allocation for those resources, then you can proceed forward. The next thing is to deploy in Microsoft Azure, you have a couple different options. First of all, you can use what we call Azure HPC. These are scripts that are designed to deploy an HPC cluster, but you have a lot of customization ability to do around that. The next one is Cycle Cloud, which is sort of a deploy your cluster in a box. They have some templates, and this is a free service in Azure if you like to use that. Azure Batch allows you to, basically it sets up a software as a service to infrastructure as a service. It's comparable to a resource manager with a job scheduler. So if you're familiar with Slurm or with PBS Professional, Azure Batch does similar work in scheduling your jobs, running them, and getting your responses, your output files back. And the last option is an ARM template, which Azure, HPC, and Cycle Cloud both use this, but you can define your resources in a JSON file and then say, let's deploy these resources in Azure.
So there is one question in Q&A.
Sure.
So how do you disable SMT and have only one hardware thread per CPU core?
All of our HPC SKUs, our HSKUs, they don't have hyper-threading enabled. So those are all physical cores. Did that answer your question, or?
Yeah, I think the person who asked the question, yeah. Sure.
And just to add to that, and we only have one VM per host for all the IB enabled SKUs. So no hyperthreading and only one VM per host.
Right. Yeah, so no VM sharing.
So there is,
the actual physical hardware.
yeah, there are more questions, but if you want to continue and come back later, that should also be fine. Or if you want to answer now.
I'm okay answering now.
Okay, so there's this question that should in the quota define also a space quota? Like is premium storage mainly local NVMe, and what parallel file systems are available for shared IO? I think if you click the Q&A box, you can read the question and choose to answer live there.
I'm trying to see the Q&A box.
Yeah, here, right? So
maybe I'm not seeing this.
Okay, I can repeat it again.
I apologize.
Sure.
In terms of the storage options, all of our HPC SKUs have a local SSD associated to them. They range from about 440 gigabytes on the HB and HC and the HBV2, and then the HBV2 has a local NVMe disk that's about 880 gigabytes that is available for use. The NV SKUs or the ND SKUs also has that local SSD. In terms of storage options, you can build a Lustre file system or BGFS file system out there. We do have an Azure NetApp files service that you can use as well for if you want to just do a standard MFS mount to shared file system. And then based on the file size, how you configure it determines what kind of performance you'd get on that. So that's that. Is there another question, or is that wrapping this up? Is that the last question?
That's it for now. I think we can continue.
Okay.
Thank you.
Great. Moving forward. So setting up Azure HPC scripts. First of all, the prerequisite is you install the Azure command line interface, the CLI, and that will help install the other things. So you need to use Bash, JQ, and SSH. If you want to just have a setup environment for you, we offer what they call the Azure Cloud Shell. So in Azure, you can go fire up a Cloud Shell, which has the CLI available, or you can deploy a Linux VM or use the Windows Ubuntu shell and then install the Azure CLI there. And right here, we give detailed instructions of how to set things up there. Next, when you're deploying Azure using Azure HPC, we give you the option to, you first source the environment variables, and then you do an init, which copies over whatever example you'd like to use and creates a directory. And then you can run this deploy cluster Azure HPC build, and then we provide some commands to connect to your environment. And just to the next stage. So for this, I need to now share my screen, Jeff, and do I need to give up remote control and share mine? Show meeting controls, right? So I'll share my screen now.
Sure. Let me stop my share. Yeah, please go ahead.
I need to allow Zoom to record this meeting. All right, I guess I need to quit now. All right, are you able to see my screen?
Yeah, we can see the screen. Thanks, John.
Great. So here on GitHub, if you go to Azure HPC, this is the scripts that we use. It's all open source. You have the ability to see what we're doing as well as configure it. As part of this demo, we're going to use the examples. And in this, we have a bunch of different examples for a lot of different, if you want to configure a BGF file system, a Lustre file system, or a Lustre file system. Environment, it'll create a cluster, and it will also configure you a Lustre or a Lustre or BGFS. For the demo, I used the simple HPC PBS example. And here you can see our configuration, our JSON file that we use. From here, we specify what region. As Jithan showed previously, there's a bunch of different regions that you can use. We indicate what image we'd like to be deployed on our different machines. what resource name. Here's where you deploy what resource type. If you want an HVV2, an HC, or an NDV40. And then we just, you can use the standard networking setup. And then by default, we create a head node and we provide 2 premium SSD disks on this, a terabyte each, so you'll get about 2 terabytes of storage. These are the scripts that we want run on the machine. Let me see, I think I just saw Q&A. No, Azure HPC does not use Batch Shipyard in the background. It uses, where we give you the option to deploy a workload manager. So this uses, though, an ARM template. It deploys an ARM template, and then we configure, in this case, we configured a PBS workload manager. Right here, we put a PBS server on it, and then on our compute nodes, we put what we call a PBS client. And so this is a configured working cluster using PBS Professional, using PBS Pro 2019. And then down here, these are just tags that run our scripts. So from there, so starting from this simple HPC PBS cluster, and that's what I did over here. Once you set up your configuration file correctly, then if you run an AZ HPC build, it'll go through and deploy the entire cluster, and it does it in a little under 10 minutes. So in this case, I'll pull up my JSON file here. I went through, I told it I wanted to deploy this in our West US2 region. I wanted to use this image for my head node. Actually, HPC image, and Jithan had made a new image with the latest MVAPage 2 and MVAPage 2X coming out in the next few weeks. We will have the latest image here that we can use and make that available with the MVAPage 2 and MVAPage 2X builds on it. I defined what VNet I wanted to deploy in. I told it that I wanted to deploy 8 compute nodes. And in this case, I decided to give it 2 terabyte hard drives, so 4 terabytes, because it will put these in a RAID 0 configuration. And then these are the compute nodes, standard HB120RS V2s. And then from there, once this was all configured, as I showed above, I did run the Azure HPC build. These are the scripts that it ran on. And then from here, I am able to do an Azure HPC connect minus you could tell which user, HPC user, and then the head node. And at this point, I am now connected and logged into my HPC cluster with 1 head node and 8 compute nodes. If you type in PBS nodes minus AV capital S, it'll show you that I have 8 machines up and available, ready to run. And so now I'd like to submit an interactive job. Equals 8 and CPUs equals 120 MPI procs equals 120. Hit enter, and now I'm now running on these 8 machines. You can see that they're all busy now with my interactive job. Now we have this demo script, which we clean out the environment. We then load MVAPage 2, and then we'll run this an OSU latency test using MVAPage 2, followed by a bandwidth test with MVAPage 2, and then at the end we then run an all reduce on all 8 nodes with 120 cores to show that performance. So to show that now, if I do and now I run demo.sh, it now is running our latency test, followed by our bandwidth test. And then finally the all reduce. So as you can see, we are, I'll wait for a second, good. So you can see that we're getting very good latencies, 1.9 for the most part for the 8. And then bandwidth test about 23, close to 23 gigabytes of bandwidth. And then finally, our all reduced numbers. So this gives you an example of how to quickly set up a cluster and then run these benchmarks. And then from that, you can now put your own scripts in and run your own MPI jobs. So sorry, go ahead.
So there were some questions. If there is a
Sure.
pause, I can ask those.
Yeah.
So first one is that does Azure HPC use batch shipyard in the background?
No, it doesn't. We use ARM templates to deploy it, not batch shipyard. You can use batch shipyard if you want. That's more for running containerized workloads. So if you wanted to run Docker, Singularity, those type of things, that's where batch shipyard would come into play. But if you're not running in a containerized environment, then batch shipyard is not the tool of choice.
Okay, and there's another question. Does the MPI MMAP2 module come with the CentOS HPC image?
Yes, it does. So if you do a module load or avail, these are the different modules that we provide. And so in this case, you do have your MPI2 as right. So those are the ones that we provide in this image.
Okay, and one last question that is still remaining. So the person asked, hello, I don't know if you already answered this, but could you share a few details about the hypervisor?
So the hypervisor is called Hyper-V. It's what's run under the hood. It's a Microsoft product, and it fires up the virtual machine. Now the hypervisor on our machines are limited to the number of cores and memory that we give it access to, so that we dedicate the rest of the hardware to the customer's virtual machine. And so earlier it showed things, Jithin was showing that we reserved a couple cores per socket or a NUMA domain. And so those are dedicated to the hypervisor. The other ones are dedicated to the
Yeah, so just
right.
like the cores are reserved for the host, so I mean, the hypervisor runs on the host, right? So hypervisor will touch only those reserved cores. It won't touch any of the VM reserved cores.
Right.
And somebody just asked that while you were running this test, he asked that, could you try to run the same test using OpenMPI? I'm not sure if you want to do it now, but.
Right. I mean, I could, but that's not part of our demo. And
right.
I think we're going to be tight on time.
Yep.
So, but yes, if you come over to Azure HPC here, we have, if you come into apps, then we give a couple different apps that we've already set up, and to do the open, we have health checks and Intel MPI. So if you were interested or open MPI, you could look into those and run the same test yourself. So
yeah, thank you. I think we can continue.
All right. So now, Jithin, do you want to? I'm going to stop sharing mine, and do you want to share your screen again?
Yeah, sure. Yeah, and just to continue, I mean, answer that question. So, yeah, OpenMPI module is also there on the image. Yeah. Okay. Let me share my screen. Are you able to see the screen now?
Yes, I can see it. So, all right. So now we've gone through a demo of how do you deploy this in Azure and how you quickly set up and run your tests in MVAPage2X. So the next one is for the data we're going to show you now. This was same type of setup using a CentOS 7.7 HPC image, using these MVAPage2 and MVAPage2 libraries with the Mellanox OFED stack. So when you plot out your results for internode latencies, we showed you right around 2 microseconds. And then as we go to the message sizes, we can see that MVAPage2 and MVAPage2X follow each other very closely, and depending on the points, some are better. MVAPage2X a little worse here on ours, but a little better here, but they trend the same line. Now, when you do an intranode or a single node or type of things, then the MVAPage2X gives you this type of curve, so a little faster performance for all the MPI messaging happening on the same machine. So that's some of the things we found, and that happens due to the XPMEM features. The next one is we showed the bandwidth. We're seeing that both MVAPage2 and MVAPage2X trend the same on our HBV2s. So not a big difference, and they are using the RPUT protocol for the rendezvous protocol. So there. And then the next one, the all reduce, we ran this on 960 processors, and we found that they tracked pretty well MVAPage2 and MVAPage2X. But right around this message size, the 256 is where we saw this departure, where we were getting some better performance in the MPI all reduce at that size. And yeah, this was run, and in this case, on 8 machines. But yes, the MVAPage2 XPMEM collectives did give us better latencies. The next test we ran was this MiniFE. Now this is a finite element mini application, and using unstructured implicit FEA codes, finite element codes, and both codes tracked fairly similar. On this code, MVAPage2 gave us slightly better performance at the higher scale, but overall, they're tracking very closely. And this is some of the information, but we did get good scaling on the HBV2 platform with both of these, as you can see. And the final application we ran was Cloverleaf. Now this is a hydrodynamics mini code benchmark that uses the Euler equations. Same thing, we saw that very good scaling, up to 32 nodes. In some cases, MVAPage2X slightly better here, slightly worse there, even here, so they're tracking quite closely. So overall, good performance. And this is the end of our showing these different codes. Answering the question. We are using, the Lustre clients can use the CentOS image coming back. The Lustre distribution, if you go look at the Azure HPC scripts, it shows you exactly where the Lustre is getting pulled from, so you can check that out. As to is the Lustre patched, I'm not aware, so you'd need to look at what version they're using and determine if there's a patch that you need. So in that, we're coming close on time, or going to the next section. We're happy to answer questions also at the end of this presentation, but for now I'll turn it back over to Jithan so he can go over the best practices recommendations. And then based on how much time we have at the end, I'm happy to answer more questions.
Sure, thank you, John. Yeah. Okay, so let me move over to the best practice recommendations. Okay, so when we deployed this, we showed this demo. Like this was actually using a virtual machine scale set. So one of the main one of the prerequisites for IB support is that when you deploy the VM or if you're using the VMSS, those have to have the same P key. Like we use InfiniBand P keys to isolate traffic from different customers, right? So when you are deploying VMs, you need to make sure that like all the VMs are using the same availability set. So if you are using the HPC scripts, like the one that John showed, they already take advantage of VMSS, and they all will have the same P key. So one of the easy way to check if they have the same P key is to like just check for this file. I mean, depending on the IB card, etc., it might be the location might be slightly different. This is just an example. But I mean, always make sure, like if you're deploying individual VMs, they all use they are deployed in the same availability set. Okay. The next one is so I mean we mentioned like with the host partitioning we don't have any interference from the host to the workloads, right? So I mean, but so this is in cloud, like there so there is a guest agent that's running on the VMs. So I mean, like in general, the guest agents do not cause any jitter, but there might be some like highly sensitive applications where you can configure like these. We can update the guest agent configuration so that any interaction from the guest agent is very minimal. So I mean, these are the settings that are exposed in the latest guest agent configuration. So we'll be putting this in the HPC images as well, so you don't really have to worry. But I mean, if you really want to, if your workload is really sensitive, I mean, you can even just disable the agent, run your job, and enable it later at any point in time, like when your job is over or when you're done with the deployment. So I mean, it's completely up to you. So you can just disable the agent for your highly sensitive workload. There are no side effects or anything. Like, I mean, the guest agent, the main use is, I mean, one of the main use cases is, say, if you forgot your SSH key, or if you don't have, I mean, if you want to reset your password, you can use, I mean, you can change that from the portal. And when you do that, the communication happens to the agent. So, I mean, those things won't work if you disable agent, but for the most part of the things, you can just disable agent, run your HPC workload, and then enable it later. So that's another thing. So, I mean, coming back to the runtime configuration. So, I mean, when you like really scale out, I mean, best practice is to use scalable transports. So the SKUs support DCT. So if possible, use that. So MVAPH2X has the env parameter env to use DC. So that enables the DC. So DC, as many of you know, it's highly scalable, and it is supported in the hardware. And all the features of RC are supported, like RDMA, atomic operations, etc. are supported. Unlike UD, where UD gives really good scalability, but you don't have features like RDMA, or you're limited by the MTU size, etc. Right? So you try to use DC as much as possible. And if for some reason you can also use, I mean, if DC is not giving you good performance, then or you can switch back to RCUD hybrid transport protocol. So MDTU's UD hybrid, you can use that env variable parameter for that. So advantage is that, okay, you have a lesser memory footprint, avoids QP trashing, so you'll get good performance and good scalability in this case. So another feature is that so you can enable adaptive routing. So adaptive routing is basically if during the communication, if one of the links is found to be like congested, then the switch automatically reroutes and tries to avoid that congested link. So on Azure, and this AR is actually configured per SL. So on Azure, all non-zero SLs have AR enabled. So to make use of adaptive routing, you can specify, say, a non-zero SL, for example, 1 or 2 or 3. So I think so. We support SLs 0 to 7, so 8 SLs. So anything from 1 to 7, you can specify and take advantage of adaptive routing. Any questions so far, or? Okay. And other best practice is.
Jitin, one quick question. So
Sure.
on the SL, so you provide the full flexibility. Anybody can run experiments with any of the service levels?
Yes, that is correct, Dr. Panda. So only thing is that AR SL0 AR is disabled. This is just to support like some, say if there is some library which some communication runtime which doesn't take advantage of AR, so they can just go back to the to the like old non-AR mode. That's all.
Okay, thank you.
Sure, thanks. Yeah, the other one is NUMA awareness. For example, like the HBV2 or the AMD ROM in general, they have, I mean, the NUMA architecture inside, right? So, I mean, your workload, I mean, so you can specify, say, for example, if your workload, one of the ranks is like really communication intensive, you can map that rank to the NUMA node closer to NIC. Like, I mean, that's a like best practice that's in HPC. So, but like these two are mainly specific for the NUMA awareness. So one thing, I mean, for hybrid MPI plus OpenMP codes, one of the best practices is to try and do like CPU binding equal to NUMA node, where MPI rank is assigned per NUMA node, and you can like do OpenMP within the NUMA node. So those usually gave the best scalability results for the current experiments. Other thing is NUMA aware collectives. So, I mean, the addition of NUMA brings a new level in the like hierarchical collective. So first you have the NUMA node, and then you can go to the socket level and then node level, right? So, so NUMA aware collectives shows to be like showing good performance improvements. So that's another thing. And the different protocols and thresholds for MIPS2. So MIPS2, more or less, it just works out of the box. So a couple of things that we we thought like it was giving good performance was, so rendezvous protocol, if we put output, if we select output, it was showing nice improvements for bidirectional bandwidth. So that was one thing, and I think like this is going to be default in the next versions of MIPS2 and MIPS2X. So the next one is enable XPMM if possible. For example, the MIPS2X supports XPMM, and we, as John showed the results earlier, like for the intra-node latencies, especially for large messages, it was showing really nice improvement. And similarly for the XPMM aware collectives, for example, all reduce was showing around 3x improvement when we enable XPMM. So one note there is that XPMM by default is not, it's not installed on the HPC VM images, but I mean, user can select and install XPMM, and that's not an issue. So because of some license issues, so we have not installed XPMM, we have not put XPMM on the HPC image, but I mean, users can do that, so that's not an issue. So with that, let's conclude. We are more than happy to take any questions that you may have. We can answer it right here.
Thank you, Jitin. So I had one question.
Sure.
Maybe I think you answered or not. So is there any support for other programming models in the Azure HPC, for example, SHMEM or UPC++ Legion?
So So in the HPC image, like it's mainly MPA libraries, but I believe HPCX, I think it has HMEM also. So I mean, but so the HPC, the current HPC image, it's mainly the MPA libraries. But I mean, once you one of the easy ways is you can use HPC image as a base. And you can build your own custom images out of it. So for example, you deploy a VM with CentOS HPC image, you install your own like libraries, whatever you want, you'd like, and create an image. You can create an image out of it, and then use that new image for your deployment. So I mean, you have that flexibility.
And a follow-up question to this
Sure.
flexibility argument that so is there a way that I can upgrade the kernels and like do low-level stuff there as well?
Yeah, definitely. Yeah, I mean the VM, like once you, that you deploy, it's, I mean, you have the complete ownership. You can do whatever you feel like. So anything you can do inside the VM. Yeah.
Okay, thank you.
Sure. Yeah. Any other questions in the Q&A side?
It looks like there is a question in the Slack.
Oh, sure. Do you have the? I don't have Slack.
Yeah, let me just read it for
Sure,
you.
thanks.
So would you recommend running MPI benchmarks as a health check test?
Yeah, I think, I mean, occasionally we may, I mean, when you deploy a large scale set, you may run, like you may find one or two nodes, like say, without IB, say, I mean, that is, I mean, that is possible, like, because these are commodity hardware, right? So it is still possible. So it's a good idea to have that scripts. I think John have some like dedicated health scripts to check the sanity. So maybe John, do you want to add more on that?
Sure. So typically when I'm doing large benchmarking runs to 128 nodes up to 300 or higher node counts, what I will do is bring up all my machines and then run a quick ping pong test and a quick bandwidth test to make sure that all of my hardware is behaving as expected, and then I will run my tests. We're doing a lot of work currently right now to make sure that every VM we give you has good network, good IB cards, good performance as expected. But as you know, doing HPC, hardware goes bad over time, and sometimes a machine or two will slip through the cracks and release the really large scale. And so to do a sanity check before you do benchmarking or other type of work isn't a bad idea. It's something I typically do once, just on the first time I bring up the cluster, but after that, then I'm happy with it.
Yeah, and it is very typical in a like a on-prem cluster, right? So yeah, I mean, users typically do that too, right? So it's always a good practice. Yeah.
Sorry, I have a question.
Sure.
So you said that XVM is not already there. So is there any instruction or something that users can install it on the node?
Yeah, I believe even MapH2 user guide also has that information. So it's the like, I mean, you can just git clone and install it. So yeah.
Okay, thank you.
Yeah. So yeah, there is nothing, I mean, I just want to add that there is nothing specific to Azure, like for any of the MPA library installation, like whatever you are running on the on-prem, like, I mean, it just works. It's the same environment. And even performance is very, very similar.
Okay,
so Jitin, I have a question on the adaptive routing. So you said adaptive routing is supported. Are you, have you people done some large scale tests and see the benefits?
Yes, yeah. So I mean, in tomorrow's talk, I'm including some of the results there.
Sure.
So yeah, yeah. So we have seen like really good improvement. And especially we ran the GPC results, and it was showing really nice improvement.
Okay.
Yeah, I mean we can we can discuss more in tomorrow's talk. I just don't have the slide in here.
No, that's fine. That's fine. So for everybody's information, Jitin will also be giving another half an hour talk tomorrow with a lots more numbers and more details.
Sure. Thanks.
Any other questions from anybody, audience? We have a few more minutes. We can for QA. Okay, so if not, then let's thank again Jitin and John. Thanks a lot for your insights into the Azure tutorial.
Sure. Thank you so much. Yeah. Bye.